Marcus, can you do a quick sound test?
Hello, hello. Can you hear me?
All good, thanks.
All right. And can I share my screen already, or should we wait?
Sure.
So we have another like 10 seconds and then I'll start the session. You can share your screen. Yeah. Right. Welcome back from the lunch. So we are starting this session. It's called Enhancing Techniques. It will have 3 talks, and the first talk will be given remotely by Marcus Anders, and the title is Sansuma, Structure-Based Symmetry Breaking in SAT. Marcus, you can go ahead.
Okay, thank you very much. And also thank you to the organizers for letting me speak remotely. If anything goes wrong, if you can't hear me or something, please interrupt me. All right. Yeah, I'm going to be talking about this new symmetry backing tool called Satsuma, which is based on what we call structure-based symmetry backing. And this is joint work with Sophia Brenner and Gaurav Rata. Now, okay, I'm going to be talking about Boolean satisfiability. And I think we've all heard about this before. So my formula is going to be in conjunctive normal form. And I presume that you know what literals and clauses and all of that are. Now, I'm going to be talking about symmetry breaking. So I should define what symmetries are. And for me, a syntactic symmetry of a formula F is a permutation of its literals such that the formula is mapped back to itself. And this permutation should also respect negation. So if V is mapped to V prime, then not V should be mapped to not V prime. Now, I have this example here. So this is quite a simple formula. And if you stare at it for a couple of seconds, I think you will spot that there is this very obvious symmetry that exchanges V1 and V2. However, we can also just confirm this by trying to apply the symmetry phi. Now, what does that mean? So we try to apply it to the formula. More precisely, this means that we apply it to each of the literals individually. And then if we just divide this out, so we apply this, we rearrange the formula slightly, we can see that indeed this is a symmetry of the formula. And this also means that we can always very efficiently check whether a candidate permutation is actually a symmetry of a given formula. Now, this is not how we usually compute the symmetry, so we don't do this on the formula directly. Instead, what we usually do is we first turn the formula into what's called a model graph. Now, the definition of this graph is quite simple. We just take each literal of the formula and we turn it into its own vertex of this graph, and then we connect the literals that belong to the same variable to each other, and then we make another vertex for each clause in the CNF, and then we connect the clause to its contained literals. And then the property of this graph is that the symmetries of the graph are precisely the syntactic symmetries of the formula that we've started with. And this example symmetry that we've seen earlier, this just maps to the graph by, we can see this exact same symmetry on the graph as well. Now, why do we do this? Why do we turn formulas into graphs? Well, because we have efficient algorithms to do symmetry detection on these graphs. Now, in particular, we have efficient practical algorithms that do this. Now, to collect a few more facts about symmetries of graphs or formulas, first of all, there can be an exponential number of symmetries in the size of the graph or the formula. And second of all, or maybe more importantly, the set of all the symmetries, which I'm going to denote with this odd f, actually forms a permutation group. And this means that if you have two given symmetries, you can just compose them and get another symmetry. And composing just means first applying one symmetry, then the other one, and the resulting permutation will also be a symmetry. And this enables us to deal with symmetry more efficiently. In particular, we can store a permutation group using what's known as generators. So this is just a small subset of the entire set of the symmetries that suffice to produce all of the other symmetries by composition. And in particular, this generating set is of polynomial size in the number of symmetries. All right, so why should we care about symmetries in the context of SAT? Well, because we can use them to solve SAT more efficiently. And I brought this, so there's lots of ways to explain this. And I brought here a small observation. So if we have some symmetry phi, and we look at any assignment sigma to the variables or literals of a formula, then it's quite easy to see that it doesn't matter whether we evaluate f under sigma or under sigma permuted by the symmetry phi. So it must give the same result. And why is that? It's just because if we permute f by phi, we just get the same formula back. So we have this notion of symmetrical assignments. So we can map assignments onto each other via symmetry. And how does this help to solve SAT? Well, okay, here's a very silly way of solving SAT. We can just try out all of the assignments to a formula. And this is just all of the 0, 1 assignments to 3 variables. And what symmetries give us is this notion of equivalence classes on these assignments. So each of these boxes are supposed to represent assignments that we can map onto each other via symmetry. And the very simple observation is that we can reduce the number of assignments we test to only 1 per equivalence class. Because in each equivalence class, we can map the assignments onto each other via symmetry. And we know that by symmetry, they must give the exactly same result for a given formula. And to achieve this in practice, there's lots and lots of different techniques that I won't have time to go into. In particular, there's lots of dynamic techniques where we try to modify our SAT solver in a way that it tries to prevent trying out symmetrical assignments. And only, it's supposed to only try out 1 per equivalence class. And what this talk is more precisely about is static symmetry breaking. And this is different in that we are only modifying our input. So the idea is that we add clauses to our input that falsify all but 1 assignment per equivalence class. So all of these assignments that I've crossed out, we will just try to add clauses that falsify them so that the only satisfying assignments are the ones, such that only 1 per equivalence class is left. And in particular, note that the ones I've crossed out here, they are precisely the ones that are not the lexicographically smallest string. And this is precisely the idea that we're going to use. So the constraints that we're going to add are given some symmetry, the constraint which checks whether when we apply the symmetry phi to our current assignment, does it get larger with respect to some lexicographic ordering of the strings. And for this talk, it doesn't really matter how this is encoded precisely into CNF. However, it should be noted that it is possible to efficiently encode this, and it might even matter in practice which encoding you use, but for this talk, it doesn't really matter. And I hope that it is sort of easy to see that if we just add all of these constraints, so if we do this for all the symmetries of the symmetry group of a formula, then this will actually give us only 1 assignment per equivalence class. However, this is obviously an infeasible approach because I've mentioned earlier that the number of symmetries can be exponential in the size of the formula. All right, so there's sort of this trade-off here. There's overhead we get by adding too many of these constraints, but we also want to get some benefit out of it. So we want to cut away as many symmetrical assignments as possible without adding too many constraints. And intuitively, what we want to do, we want to choose sort of a nice subset of the symmetries that give us a lot of benefit without much overhead. And okay, I should mention that the precise ordering that we use is important as well, but I'm just not gonna talk about it. All right, now a natural question would be, how does the state-of-the-art tool do it? So which nice subset of elements does the state-of-the-art symmetry breaking tool choose? And So the state-of-the-art static symmetry breaking tool is break it. And now I've listed here some of the heuristics that it uses. I don't expect you to understand all of them. This is more meant as an overview. So first of all, it just uses the generators returned by the symmetry detection tool. So that gives you some set of generators. And for these generators, then these Lex leader constraints are produced. And on top of that, there's also more heuristics that try to obtain nice elements or nice constraints. And I'm not going to dive into this. And I want to now get to our new tool, which is Satsuma. And the thing I want to mention is that on the surface level, it's fair to say that it's a re-implementation of Breakit. So it uses a lot of the same strategies, and it more or less just tries to build on top of Breakit with some new ideas. And so I think it's sort of fair to say that like half of the implementation is just a re-implementation with some new engineering, where the motivation of the new engineering is to reduce the computational overhead of the implementation. And then there is another part, which is new ideas, which is the part that I'm going to talk about in this talk. And this is also the main contribution of the paper. And these new ideas are that we will try to detect very specific structures in the symmetries of a formula. So it's these, so the list here, it says row symmetry, row column symmetry, Johnson symmetry. These are different kinds of structures that we can find. And this is what I'm going to talk about. Now, on a high level, this even works like this. So you start with the formula, and then these new detection algorithms are applied. And these new detection algorithms then produce a remainder, so stuff that was not detected by these special structure detection algorithms. And only this remainder is then fed into what's essentially a Breakit reimplementation. Okay, so I'm gonna now talk about these new detection algorithms here, but in order to do so, I will have to provide some kind of tools to deal with groups. And if you've seen my talk last year, this is based on the same kind of idea that we want to make use of the graph of the formula. Now, okay, so how do we do anything with groups? Now, the tool that we're going to use is called pointwise stabilizers. And I'm going to explain the idea of pointwise stabilizers, but it's fairly simple. So on the left here, I have this 4 cycle, and I think it's quite easy to see that you can move any of the vertices to any of the other vertices. For example, we can rotate it, and with the rotation, you can see that any vertex can go to any other vertex. And I've sort of illustrated this with this orange box. This orange box represents the orbit of the vertices, which just mean precisely what I've just said. Any vertex can go to any other vertex. And on the right here, we've taken the pointwise stabilizer of the vertex on top. So this is marked with this X. This means that we've performed a pointwise stabilizer of this point. Now, pointwise stabilizer means we can't move this anymore. So this one is stabilized. So symmetries are not allowed to move this point anymore. And what this results in is the orbit partition that I've shown here. And if you think about it for a second, you can see that only one symmetry is actually left, and the symmetry moves these 2 vertices here. So this is the reflection on the y-axis, essentially. And these pointwise stabilizers are actually the only tool that we're going to use to analyze the formula for particular structures. But okay, I've sort of lied. We're not actually gonna use pointwise stabilizers. So pointwise stabilizers, we can compute them fairly efficiently, but in practice, it's not that fast. So it's the Schreier-Sims algorithm, and it has some drawbacks. And instead, we're just gonna approximate pointwise stabilizers using what's known as the individualization refinement paradigm. Now, for this talk, doesn't matter what that is. It's good enough to know that we just approximate pointwise stabilizers. However, I should mention that this IR paradigm, this is what's being used by the general purpose symmetry detection algorithm. So it's sort of a very natural choice to use this for these special symmetry detection algorithms. And one thing to note is that we're just going to pretend like this approximation is good. So We just pretend that the approximation will give us the pointwise stabilizers. And why is this okay? Well, it's okay because in the end, we can just check whether the structure that we supposedly found is actually a symmetry structure in the formula. I've talked about this earlier. If we have a candidate permutation, we can efficiently check whether it actually is a symmetry. And this is why this approach is correct. We just, in the end, we do this check for a certain set of candidate permutations and ensure that the structure is actually there. Okay, well, let me get to the structures now. So the first structure that I'm going to talk about is row symmetry. Now, one note on these illustrations here. So these illustrations are not necessarily the graphs that we look at. This is an illustration of the group, meaning that the graph may be more complicated. There may be stuff attached here. And what these dots represent is the variables of the formula. And I'm going to talk about how these get moved by the symmetry, so by the group. And again, these colored boxes, these are supposed to be the orbits that I've talked about earlier. Now, what is row symmetry? Row symmetry means we can arrange these variables or these dots in a matrix such that the rows of this matrix are interchangeable by symmetry. However, the columns are not interchangeable, only the rows. Now, why should we care about this structure? Well, first of all, this structure is already used by Breakit, and for good reason. And the reason is that for this kind of structure, we have efficient complete symmetry breaking constraints. So if we know we have this structure, we can just write down this essentially perfect constraint and be done with it. Now, okay, last year I've talked about the drawback of the particular detection algorithm of Breakit. There are some downsides to the algorithm there. So let me now talk about how we detect it in Satsuma. And actually, the approach is quite simple. It uses the pointwise stabilizers that I've talked about earlier. And the observation is actually surprisingly simple. We just pick one of these columns, an arbitrary one. And for each vertex V of the column, we then pointwise stabilize that vertex. For example, in this illustration here, I've stabilized the vertex on the top left. And when you think about it, what happens then is that we can't move this row anymore, because in row symmetry, we need to move the entire row at once. That means if we stabilize one of the points in a row, this will stabilize all of the other vertices in the row as well. And this is how the algorithm works. We stabilize one of the points, and then we collect all of the other points that got stabilized by this action. And this will give us our candidate rows. And then once we've created this structure, we just verify that this is actually the symmetries of the formula. Because we work with this approximation, we need to make sure this is correct. And we can just do this by testing certain permutations of the rows. All right. And then, as I've said, knowing that we have row symmetry, we can produce this efficient complete symmetry breaking constraint. All right. So let's get to a more one thing I wanted to mention is that, okay, I've only shown the pictures here. So this is a wall of text. You don't need to read it. What I want to say is that in the paper, we prove that this is correct. So we prove that success only hinges on the correctness of this approximation. And we also do this for the other structures that I'm going to show, but I'm not going to flash the theorems. Just want to mention that in the paper, we do this formally. All right. Now, on to the next structure. This is row column symmetry. And I think from the name, you can already guess what it is. So again, this means we can arrange the variables in a matrix shape, and then the rows of the matrix are interchangeable, but also this time the columns are interchangeable arbitrarily as well. And this is row column symmetry. Now, this has been studied quite extensively. So row column symmetry has been studied quite extensively, and it has been argued long ago that row column symmetry occurs naturally when you model certain things. So for example, if you have a relation between two different objects and these two objects are arbitrarily interchangeable by symmetry, then you will have a row column symmetry. For example, pigeons and holes. You've heard this before probably. Now, this is often considered in manual symmetry breaking, and actually we know quite a few different incomplete breaking constraints for these sorts of groups. For example, there's double legs or snake legs. However, we also know that efficient complete legs leader constraints are implausible to exist for row column symmetry. So this has some complexity theoretic implication if these were to exist. So, okay, we can't break them completely. However, we do have some nice results that we can use once we've detected row column symmetry. We can just insert this double legs constraint or the snake legs constraint or some of the others that have been proposed. Okay, so how do we detect it? Again, we just make use of pointwise stabilizers. This gets slightly more involved, and I don't know how intuitive this is anymore. But if you stabilize one of the points, again, stabilize the one on the top left, then this will identify its row and column. And then there will be some remainder that still operates like a row column symmetry. And the idea that we use is we then use this row and column of the first vertex sort of as a coordinate system of the rest of the vertices or variables. So we first collect this first row and column, and then we use further stabilizations to sort of identify, oh, this variable, it is in the row of this blue vertex and in the column of this other purple vertex. And this is just consecutive stabilizations that we use for this. All right. On to the last structure. And okay, no, sorry. I should mention that the constraint we then produce once we detect row column symmetry is this double legs constraint. Okay. On to the last structure, which is called Johnson symmetry. And I'm not sure how intuitive this is anymore. So on the right here, we have this circle, this orange circle of dots, and this is supposed to be the variables. And this complete graph on the left, that's just meant for illustration. Now, these variables, they correspond to edges in this complete graph on the left. And the symmetry, this acts like we permute the complete graph, and then the variables, they get moved like the edges of that complete graph. So this is sort of an induced action of the symmetric group on the two subsets of the vertices of that graph. And now you might be thinking, oh, well, this seems oddly specific. Should we really care about the symmetry? And maybe surprisingly, I think we've sort of talked about Johnson symmetry today already. So Stefan mentioned in his talk SAT-modulo symmetries. And in my eyes, SAT-modulo symmetries is a very efficient tailored algorithm for dealing with Johnson symmetry. And it's not just SAT-modulo symmetries, there's also breaking constraints for Johnson symmetry. And this is, in general, a well-studied type of symmetry. Now, again, we know that efficient complete legs leader constraints are implausible for this, but as mentioned before, we can just make use of some of the literature on these types of groups and produce one of the constraints from the literature. Now, how does the detection of Johnson symmetry work? Well, this gets slightly more involved. So I have this illustration here, and I've said that the variables, they correspond to the edges of a complete graph. And the idea is then that we stabilize the edges in the complete graph, and this partitions the remaining edges into the ones that are incident to the edge that we've stabilized and the ones that are not incident to the one we stabilized. And then we sort of intersect these sets in a more or less clever way to try to find out where the variables belong in the graph. All right. And some more brief, some brief information about the implementation. In practice, we don't just want to detect these particular structures that I've shown. I think we also want to know whether we are dealing with a combination of these structures or something that is almost the structure that I've talked about. And the implementation has some extensions of dealing with combinations and relaxations of these groups. However, this might not be as sophisticated as it should be. So I think maybe there's some room for improvement. anyway. Of course, my talk is about a practical tool, so I should end by showing some benchmarks, and I will do so. And what do these benchmarks do? Well, we compare Breakit to Satsuma, and we do so using the Sats over Cadical. So this first column here, it shows the performance of Cadical on some benchmark families, then Breakit and Cadical. So when using Breakit as a preprocessor to Cadical, and the last column shows Satsuma and Cadical, and we've split this up into the preprocessing time and the SAT solving time. Now we test this on families that do exhibit symmetry. So these are from the symmetry breaking literature, essentially. And particularly, we are interested in, do these structures that we detect actually make a difference? So is there some benefit to be had? And we can sort of partition these families into the kind of structure that they actually observe. So first, there is the two families that observe Johnson symmetry. So these are these clique coloring instances and the Ramsey instances. And in particular, for both of these, it's actually true that the remainder is empty. So we are not using this breakage re-implementation at all. This is just using the tailored detection of the structures. And for both of them, we can observe quite a significant speed up in the SAT performance. So we solve more instances, which is quite nice. Now, for these other structures, the results are not that positive. So if we look at row-column symmetry, which would, for example, be pigeonhole principle, as mentioned earlier, we can see that the SAT performance is actually very similar. However, Breakit also already solves all of the instances of these sets. So maybe these instances are just not hard enough to see the benefit of actually detecting row-column symmetry. Now, lastly, there is the coloring set. So now I've written here that they contain lots of row symmetry, and that is true. However, the symmetries of these graph coloring instances, they are actually more complicated. So there is more sporadic symmetry, and sometimes even other structures are in there, and we can at least see a slight speed up in the SAT performance. And lastly, there's two instance classes with no discernible structure. So these essentially just compare Breakit to the Breakit re-implementation, and we can see that they are quite similar in performance, at least in SAT performance. Now, we've done the same benchmarks with Crypto Minisat, and the results are essentially the same. Now, one thing you might have caught on is that these pre-processing times for Satsuma are actually much faster. So there's a big improvement in the computational overhead of the tool. In particular, for these graph coloring instances, there are two that just time out for Breakit after 10 minutes, and Satsuma averages 1 second on these graphs. Now, we've done some further testing on the computational overhead. So this only shows the pre-processing time and not the SAT solving time. And this is sort of an ablation study. So we've tested one family for row column symmetry, one for Johnson symmetry, and one for no discernible structure. And you can see in all of these that Satsuma is actually asymptotically faster than Breakit on these instances, at least on these sizes. And one thing to note here in this last set, you can see that there are quite a few spikes into the timeout for Breakit. And this is actually not Breakit being slow, it's the general purpose symmetry detection used by Breakit that is being slow and not capable of solving these graphs efficiently. All right, on to the conclusions. So today I've talked about a new symmetry breaking tool called Satsuma. I think we've demonstrated that detecting and exploiting richer group structures is a viable approach. Or in particular, these Johnson symmetries can be beneficial if they are to be found in the instances. And across the board, the tool is able to significantly reduce the computational overhead compared to Breakit. Now, okay, I don't consider this tool finished, so I still have some to-dos on my list. For example, I think that there can be some more group structures that we can detect. For example, the tool doesn't nicely deal with negation symmetry. But if we have some structure plus some additional negation symmetry, I think that the tool could do a better job of detecting this. And also, I would like there to be more options for breaking. I mean, One of the nice parts about this approach, in my opinion, is that you can connect this automated symmetry breaking with particular results for very particular structures. So it would sort of be nice if we can just swap these breaking constraints out with a flag. So for example, switching from double legs to snake legs for row column symmetry or things like that, or even connecting it to dynamic techniques. Then I think it could also be interesting to try these algorithms in other domains. So for example, I know that there is very recent work on row column symmetry in SCIP. There's also an implementation of the detection, but it works very different. And I think it could be interesting to try it out in these other applications. And yeah, so one crucial feature that is missing from the SAT implementation is that Breakit actually has very PB-based proof logging, and Satsuma does not yet have it. And I think it would be cool to re-implement this in the tool. I don't think this is a major hurdle. This can just be done with some work. And then, of course, doing more benchmarks or just seeing how well it does in the competition would also be nice. All right, so of course the code is freely available and open source, and I would be happy for you to try out the tool. And if you do so, please send me how it goes. So in particular, if it doesn't go well, yeah, please talk to me. And yeah, thank you very much.
Right, thank you, Marcus. Perhaps one quick question. We don't have much time.
Thanks for a very nice presentation. In one of your results, you mentioned that if your graphs are of a specific type, then you're guaranteed to find the row symmetries. Now, given that your graphs are coming from a CNF, do you know if there's structural properties on the CNF that guarantee that you're going to be able to find it, or is there something there can we bring this theorem back to the CNF world?
So unfortunately, you can just very easily model arbitrary graphs with CNF. So this there is no way of showing that all of the CNF graphs are Tinhofer because it's just not true. And it's actually very easy to construct some that are not. But it's not true, unfortunately. But it is a very practical assumption that in the general purpose symmetry detection world, we use this assumption sort of anyway, because if it doesn't hold, then the algorithms would be much more inefficient. And but yeah, there's no theory to be had there, unfortunately.
The structural properties of the CNF. So if we translate this property back to CNF, we don't. Not a clause of formulas that would have this property, or.
So the property is more involved than it looks. So this property is actually it comes from relaxations of integer programs. So yeah, I think we should take this offline. It's more involved. I think.
Right, thank you. Let's thank the speaker again.
Thanks.
So the next talk will be given by Armin Bire on causal congruence closure.
Test, test, yes. Fine. Yes. Okay, so I'm going to talk to you about something which I would call it like finally solved. So this is like some old problem, and well, I'll show you why I revisited it and what is it about in a minute. So this joint work with Katalin, who's here somewhere, and Matthias and Niels. And okay, now need to press the thing again. And so first, let me explain the problem and also give you maybe an intuition what this is about. So look at this circuit. It actually consists of two identical circuits. So there's this one on the right and this one on the left, and they're identical. And this XOR there on top compares them. So it's actually not equal, right? And so if these circuits are not equal, you would produce a 1, okay? And this is what I'm asking. Is it really true that they're different? And so if I now do a Z18 encoding, which you see here, and give this to SAT solver, it should be unsat, right? And this looks like a silly problem, in particular in this case, because this is two identical circuits. So you see like G7 has the same inputs as G8, G5 had the same inputs as G6, and these two if then else, so these are maxes or if then else, they also have exactly the same input. And so if you think about it, right, so in sense, you can just merge them and they're the same, okay? And so if you want, this is a litmus test whether SAT solver can actually solve these instances of formulas fast. And of course, already 15 years ago, we figured out it's not the case. So CDCL solvers don't work for that, for this stupid problem. So this is called, I hardly see it, it's called isomorphic miter. So this is called a miter. And isomorphic, we mean, well, we're comparing two identical circuits. Okay. And on the left, you see somehow actually how we think later inside of the algorithm about it. So it's more like actually equations, right? And the difference between this and this is this could be cyclic, right? Well, this one, of course, is usually non-cyclic. Some people in the past took the effort of trying to get back sort of from this C of C and Fs, this circuit, right? But if the circuit is really required to be cycle-free, right? It's actually a very hard problem to extract from a CNF and a DAG. Now I'm lost again, the focus, sorry about that. Yeah. Now, how can you solve this? And we have papers on this, like actually already 2013. This paper has an acknowledgement to Knuth because he helped us to fix terminology. There's one simple way, which is also actually goes back to Fahim Bachus, who probably observed this the first time, but in an AI context, so probably not for this miter. So he said, like, you should just do hyperbinary resolution as preprocessing. And in case you don't know what that is, so you see it here at the bottom. So hyperbinary resolution is the following. So you take one long clause, we're going to call them base clause, so a non-binary clause, and then you resolve in as many binary clauses as you want. And then it's required that the resolvents at the end should have, the resolvent at the end should be a binary clause again, okay? And the way how this is applied here is, I'll take the Z18 encoding you see here this is clause 24. So this is from this gate here, G7, from this AND gate. I take the large clause from that one and I resolve it against the binary clauses of the other one, which is semantically the same. Say the output A2 actually is equivalent to A1. That's what I want to show, right? And I guess because it's completely symmetric, I can do this also with the other gate, right? And then you see what I have here at the bottom? Well, this is just the equivalence of A2 and A1, right? So in principle, this is some old observation. If you do this hyperbinary resolution until completion, and you can do this actually through propagation, but this is a completely different story, then you will learn in principle the clauses you need to kind of show the equivalence sort of when you go up. So this breaks, of course, for these XORs, but I come back to this later, and also for this multiplexer. But if your circuit only contains AND gates and negations and OR gates, actually this would show at the end that sort of these two M1 and M2 are equivalent, and then you get a like conflict. Well, not completely true, and this is the subtle thing. Well, you can continue this recursive sort of like matching only if you really sort of replaced here in the upper part. So for instance, after you derive that A2 is equal to A1, here in G4, in the clauses of G4, you will replace A2 by E1, right? And that's done through substitution. But before I come to that, let me show that this hyperbinary resolution is, of course, just like ordinary resolution, just a couple of steps. All right, now so the substitution, this is the third important concept, so isomorphic MIPERS, hyperbinary resolution. And now what I just claimed, this actually only work if you eagerly do kind of substitution. And this is a well-known technique in SAT solving. So you just find like the equivalences or maybe actually transitive equivalences of two literals, right? And then you substitute like maybe the larger one by the smaller one. Now, the point is these miters can only be solved if you really do this eagerly. So whenever you find sort of like hyperbinary resolvents of like two gates outputs, you need to really substitute it in the rest of the formula. And this makes this whole process actually pretty difficult. All right, so here this is once the summary of this whole thing. So once again, we're doing this hyperbinary solutions. Then they can be done in principle through root proofs. And then you also need to interleave this with substitutions. Now, the fourth concept is structural hashing, because actually, if you think about it, if you're like for instance, you present this in AIG or some other circuit representation, and you would have a parser of a file format where this like miter is stored, and you parse it, and whenever you find like a node, you would actually first check, didn't I have seen this node before? Okay. Then you would, while you parse, actually merge all these input and output. So through a concept which is called structural hashing, you would actually solve these miters on the circuit level actually trivially. So it's just parsing the file. And this structural hashing has a long history. So it's hash consing in Lisp, common sub-expression elimination. In BDDs and AIG libraries called a unique table. And it's wrongly assumed to require an acyclic representation. Like I mentioned this already, so in like if you have these triplets from Stallman's procedure, you can have them cyclic. And last but not least, and this explains the title of this talk and this paper. Well, that's what used in concurrence algorithm, concurrence closure algorithm in SMT solvers, which is one of the main working horses in the core loop of an SMT solver. So this is how they communicate between theories. And you see it here. So this like you have some sort of like function application on two objects, and then you kind of derive that these arguments are the same, and then you know that the outputs are the same, right? And so if you apply this rule until completion, you also solve these miters. And this uses hash tables. So this is why in AIGs you hash kind of the right-hand side to the left-hand side, and then if you find another right-hand side, you look it up and see whether it's already left-hand side in the hash table, and if so, you know that it can replace one by the others. All right, however, well, first of all, these isomorphic parts might emerge during in-processing. You do some optimization, maybe CDCL solving, and only then you have isomorphic structure. And furthermore, we have many instances already in CNF. So this is the reason why we want to sort of simulate structural hashing on the CNF. And I explained to you how in principle you could do it with this hyperbinary solution. You just generate all possible hyperbinary solution. You kind of somehow interleave it with the equivalence literal substitution. And then at the end, you will solve these miters. However, for XOR and if then else case, this doesn't work. We'll come back to this later. So the first contribution of this paper, which was in an old solver of mine, which was called Lingeling, is the simple probing which partially solves that, but not for XOR and if then else gates. And last but not least, you can also read up in this old paper, CDCL doesn't work, surprisingly, for these miters. All right, now I got, well, why do I revisit it? And I want to share this email I got last year. All right, I got somebody from a company sent me email. There was in this company, there was they of course applied SAT solvers to competitions, and they applied it to one instance. And this colleague has encountered an unsatisfiable benchmark from the 2014 SAT competition that's solved immediately, right, by Lingeling, which is a solver of mine from 2013, but is kind of not solved by any newer solver. Okay, why? Okay. And then I looked at it, and well, thanks. And I already was suspicious. So this is probably the simple probing. This is one of the big things which is different in Lingeling and in Keysight, Cadogan, and all the other solvers. And it is because I figured out a couple of minutes later, yeah, so the benchmark he sent me was exactly this one, which I submitted in 2013 to the competition. And all right, so I'm now showing you first contribution, the algorithm implemented in Lingeling, which solved it. And then we'll see that it's not that powerful as the real contribution of this paper, which is concurrence closure. And but it was like a big step, and explains why there are these instances where sort of Lingeling is much better than any other solver. All right, so here's the simple probing. I have a couple of algorithms, and there's no time I can go over them. But maybe maybe I can explain the flavor of this algorithm. So you see here already like a working set, like the candidates of literals actually. So you try to find literals which are the output of an AND gate, right? So you try to find AND gates for literals, and therefore you have as a working set the potential candidates for outputs of AND gates. And while this set is not empty, you try to find base clauses, as I explained, like these ternary clauses, for instance, for ternary clauses, the same works for larger clauses. With this L, because that would actually be, if you know the Zetian encoding, really be the output of this AND gate, right? Or OR gate, or NOR gate, or NAND gate. And then you have a counting argument. You try to just to find the necessary binary clauses with some sort of matching here. And if this is the case, right? So you found enough of these binary clauses, and you don't have this hyperbinary resolvent, which you get through this process in the formula, then you add it, and then you immediately search, oh, is there the matching one which would make this an equivalence, right? Also in the formula, and if so, you found the equivalence of L and R, right? And you can easily substitute in all clauses this L by R. Okay. And this gives you sort of this running time. What you see here is the default version of Lingeling, right? This is the red one here. And if you disable here this simple probing, so nodes probe simple here, then you lose quite some benchmarks. If you run it until completion, which means you kind of do nothing else in the solver and you don't have put any limits, you solve almost all of these benchmarks. So what are these benchmarks? Well, this was the set I submitted like in 2014 to the competition, and which is still regularly used. So that's why I'm used it also for this paper. Okay, so this almost solved the problem, right? For, still, it's not really like nice because you see, and actually this is the concurrence closure version. So you see the concurrence closure I'm going to present next actually has here a flat line, right? So these trivial, these formulas are sort of now trivial. So if everybody is using now KeyStat next year as a template in the sub competition, these benchmarks will be removed from the competition because they became trivial. And so I'm going to explain now how to get sort of from this green line, which is the KeyStat without this concurrence closure, to this kind of you're solving all in zeros, almost no time, right? Okay, and for that, the basic idea is we're just extracting AND gates. So we kind of do something stupid. So we just go into the formula and try to extract gates. And we do this syntactically. Now, here's the not completely trivial, but still a basic version of that, of extracting AND gates. So the non-trivial part is here about counting, right? So you again go through some base clauses, right? Clauses which are candidates for forming the Zetian encoding of an AND gate. And then you do some counting argument, and then this counting argument lets you decide, okay, yeah, this is an AND gate, and if so, you just extract it. However, this doesn't scale, actually, so there's a way more sophisticated version in the code and also explained it in the appendix of the paper, because we want to run this really until completion on, say problems with 10 million clauses. Okay, and the XOR, on the other hand, looks way more complicated, but there's literature on this one, like in Mate Soch had almost the same algorithm. It has been like in preprocessors, for instance, for years now. And this way you can just extract XOR gates of kind of arbitrary length, actually. Okay, so these two would now go into the Zetian encoded CNF and give you sort of like these triplets, right, like gates. And then there's the last one. This is also not described in the literature before, at least I haven't found any, but I implemented a couple of times. So this is an if then else gate, like a max. This is where this max is on top with the 3 inputs. extraction, and there you kind of need to sort of find matching four matching ternary clauses, and you start with the base clause, and then you find like four matching. Sorry, in total 4 matching clauses. You find for this base clause you need to find 3 more matching ones, and then you add this gate. This one was particularly slow, like in this basic version, and actually our industrial collaborator here was interested in something similar, and this triggered here the following, this algorithm here, with this code, but I'm not going to explain the code. How do you find if then else gates? And well, we found this concept of conditional equivalences. So this came up in some sort of like hyperproperty checking for security, and it can be used for if then else gate extraction. So right, so this is an if then else gate. I hope you're fine with this notation with the question mark. So L is the output, and then if C is true, then part, otherwise else part. This can of course be decomposed into this kind of two, like not clauses but two formulas, right? Obviously, right? So if C is true, then the left-hand side is T. If C is false, the left-hand side is else, okay? And so what could be an algorithm? Well, you kind of now take as a working set, not the base clauses as we did before, but you go over literals, right? And then if you have the candidate C here, so you go over the potential condition literals, right? You go over all ternary clauses with C, and you go over all ternary clauses with not C, and you find all these conditional equivalents with like either C or not C. And then you merge these two sets, right, in an almost merge sort style algorithm. And this has then complexity, which is really linear in the number of if then else gates you extract. So here's still a high level version of it. In order to make this really linear, you need like sorting in some other arguments. But in principle, this is really a very efficient, can run now on all benchmarks competition in no time. Okay, now here's the main algorithm, the main contribution of the paper. And again, this is not that trivial, and it's also not like missing a couple of optimizations, but maybe let me just explain some important points you can also look up in the paper. So first of all, this uses always a union find data structure. You might know about this one. So you keep like one representative for one literal, and you kind of think of all the other literals which are equivalent always mapped to this representative one. And this has a merge operation here, which merges sort of the larger literal with a smaller one. And as in this concurrence closure algorithms, you first get sort of the representative of those two you want to merge, and then you merge sort of the larger one to the smaller one. So you set like these representatives to this smallest of these literals. And then, and this is kind of new here, if you have done this, then you add those literals which you merged to this working queue. So Q will be the queue where we kind of try our concurrence closure on. And so initially it's empty, but then we go through the, like through all possible gates we extracted before here. And merge the literals which have the same right-hand side. And this is, of course, done with hash table, right? Okay, so this fills our queue. And then while the queue is not empty, we're taking out all the gates we still have, which have one of these literals in the queue in the right-hand side. Okay, and positively or negatively. And now we're rewriting, so this is the substitution part, this right-hand side and the left-hand side according to this representative substitution. So it's the same form of substitution we actually saw in Niels' talk. It maps literals to literals, but potentially also to constants. And then we kind of eagerly first remove this old gate, which is now rewritten. But before we add this rewritten one, we simply check first whether there's a matching one. Matching means a gate also which has now, after rewriting, the same right-hand side. And if so, we match the two. We say that the two literals, the left-hand sides of this rewritten one and this one are should be merged. And this continues like that, okay? This is basic concurrence closure algorithm. And At the end, you need to actually remove clauses, because if this is successful, particularly on these big 10 million instances, you actually remove half of the clauses, so 5 million clauses. So this thing here removes then 5 million clauses in one line. And at the end, it's also actually pretty tricky that you need to kind of actually normalize those with respect to the substituted ones. All right, and this then gives this results, where I could stop now, and I still only have like 5 more minutes. So this version really gives you now solve these guys here immediately. If you disable concurrence closure, you get this red line, so you cannot solve all of them. And if you switch off another optimization, which is semantic SAT sweeping, and this is explained in our FMCAT paper, which is upcoming, then you lose even more, okay? And note again, these are really trivial problems, and KSAT is already optimized for these problems, so the other SAT solvers are much worse. All right, now, but we didn't stop there. So we have actually 2 dimensions where we extended these experiments. And one experiment is kind of the real reason why we're looking at this, is we're comparing 2 circuits like this one and this one, which are not identical, right? Why are they actually equivalent but not identical syntactically? Well, these are if then else, right? And we have here one negation at the output and negate all the inputs. So this is clear that these 2 if then else are the same. But you're getting like the thing here on the right? You're getting all these clauses. And so we call this non-isomorphic miters. And actually in the experiment, and also already back in the submission to the competition in 2013, we optimized simply these miters, these circuits we get with this state-of-the-art synthesis tool, which does some optimization. And this is the optimization we used. And there, the difference is not that much, right? You still gain something here by using this concurrence closure. And you also see that this sweeping here is actually more important here because here there's a bigger gap, right? But this is in the FMCAT paper. And the sweeping alone doesn't solve these because it's enabled in the default version we saw on the previous plot, right? That it's not solving those isomorphic miters fast enough. All right, then the second dimension where we extended the experiment was this one. So actually the benchmarks come as an AIG in IGO format. So they look like that. So each circle here is an AND gate, and these black dots here, these are negations. And you can, of course, trivially encode, these are only AND operators, right? Encode them into here, these Dimex formula. Each node here gets 3 clauses, right? And then at the end, you also put here that this is true, and this simplifies to clauses, so that's why it's a bit less. And now what we do is, well, this here is, if you have been working with AIGs, you would see immediately this thing here is actually an XOR, right? So I don't need to encode the 22 and 20. So I could, because I know that 24 is an XOR of 12 and 18, I could just treat this as an XOR, and this gives me these 4 clauses, right? And the same is true here for these 2 multiplexers. So this in if then else. If I see that these are multiplexers, I can also get like just these ternary clauses. And sorry, this was wrong. So this XOR here is these lower ones, and these 2 are from the 2 maxes from the 2 if then else here. Okay, and so kind of while you encode, encode the formula, okay, you match for XORs and if then else, and this gives you a more compact CNF. All right, and there it looks similar. So here I give now more versions of KSAT, and you also see that so this XITs and this, they are just like both the encoding with if then else, the XITs encoding and XORs can also be found immediately to be unsatisfiable, these miters. And if you disable now, for instance, the extraction of if then else or XORs, actually you immediately go down here. And of course, if you switch off no concurrence closure or even sweeping, you just go down. So all these techniques are important to reach this sort of straight line. and then we can also mix these two, but maybe I'll skip that as these two, the XITs and ANDs encoding, and also look at optimized circuits. All right, and this is the plot from the paper, and I have to admit it's a bit hard to read, so I'm not skipping that. In the paper, we spend quite some time to try to explain this, so let me just skip it. One thing we have in the paper, and which I want to show you, is like a comparison with other solvers, and you can really see there's like Minisat can hardly solve any of this. So plain CDCL does not work even with preprocessing. In also 2013, we had a paper which was using block clause decomposition, actually also motivated by this problem, and it gets to here. And this green thing here, this is the kind of first contribution because it was not described in the literature before, which is the simple probing, right? And then there are these two straight lines, and here you see for the first time a circuit tool, which is ABC. So ABC is the like has the state of the art for these miters. It would get actually original circuits, so it would not work on CNF, right? And on optimized circuits, right? This was pretty surprising when I saw these results. We actually beat ABC here, right? So ABC is a tool, an industrial tool, which is used for industrial scale tool, which is built exactly for this purpose. And if we just blindly encode these miters into CNF and use this algorithm, we're actually beating ABC. So this is also true in actually on 5 particular hard miters, which were used here in these 2 papers, where our conference chair is one of the co-authors, to kind of showcase the latest development in improving here this SAT sweeping, which uses directly on circuits. Here, clearly KISAT is a bit behind ABC. We'll have on the next slide some surprising effect too. However, I want to show you also that we can produce proofs which ABC cannot do, and also checks them very fast, actually. All right, so the surprising thing here is this number here. So there was one instance where even for this hard miter, this was this test 02, KISAT was just like 1.7 seconds, and this is a big one, and ABC was struggling a lot. And then we figured out, well, it's just sort of a generalization here. This was our analysis of this thing here. And obviously ABC didn't see that, like this was just a very big one. So my actually conjectures, which we don't know, that they just encoded BDDs in 2 different ways. Once where they put the negation at the outside and one where they don't do this. And then our kind of XITS encoding plus this gate extraction normalizes these if then else and would just really go one by one through them and hash them. All right. And we also have some improvements on the SAT competition, but that was not the focus. So let me conclude. Okay, so this is the first approach after I would say I worked on this for 15 years, which instantly solve these benchmarks, right? And it's run until completion, really, every time there's a probing. So you really extract all the gates you can find, which required quite some engineering. And you can read more about this in the paper. There's quite some optimizations going on. It complements this semantic sweeping. This is more similar to what these commercial or tools or probably the ABC tool is doing. But I refer to the FMCAP paper for that. It works also on other benchmarks. There are many congruences actually in the competition benchmarks. So you can, like for instance, this BMC exam benchmarks from Amazon. So they obviously did not, because it finds these isomorphic circuits. So they did not do the structural hashing when they encoded them. All right, so we want to extend the paper with description of all optimizations, and Matthias Fleury is working on a port to Catechol. So he has it almost done, so we're going to have this also in Catechol. It's clear we're only doing syntactic extraction, right? And it's an open question how you turn like more semantic extraction cheaply into this algorithm. And we don't know at all how to do linear proofs for that, or it's very hard to do this. And so this concludes my talk. Thank you.
So we are running a bit late, so one quick question.
Yeah, so other than the congress closure, any other kind of in-processing, is it possible to do that within the loop?
Yeah, this is done every time in processing too. So that's what I meant. You had to get this gate extraction so fast that every time you do probing, actually kind of in processing, you would run this complete extraction of gates. And this is actually the interesting part. So it would actually find lots of them also later during the run. So my claim that this emerged during in processing is, you can see it in the benchmarks.
Okay, let's thank the speaker again. So the next and last talk of this session will be given by Robin Coutelier about laser implication in chronological backtracking.
Hello, hello. Thank you. Hello, everyone. My name is Robin, and this is joint work with Matthias Fleury and my supervisor, Laura Kovac. And we're going to talk about chronological backtracking in SAT solving, of course. And basically, we are going to work with invariants. So we will classify different variations of chronological backtracking using those invariants. And further, we will introduce a new version of it, which we call lazy strong chronological backtracking. This was implemented in a brand new SAT solver written from scratch called NapSat, but also in Glucose and Calico, and everything was experimented on. So I assume everybody is familiar with non-chronological backtracking, but I will still show an example so we get familiar with the notations. And why I say greedy is because in non-chronological backtracking, we backtrack as much as we can until the clause is still propagating. Okay, so my notations here. We have a bunch of clauses, and the two first literals that are underlined are the watched literals. So in chronological in CDCL, usually you would make a bunch of decisions represented by a new decision level, which is a step. And on the left side, so to will be the literals that are already propagated, and on the right side, waiting to be propagated. So far so good, nothing very interesting happens. We propagate V1, V2. But when we decide V3, it gets interesting because, where is the pointer? There. The clause C2 and C1 will propagate V4 and not V4 respectively. So we have a conflict. And usually what you would do is you backtrack here, you learn the new clause, V1, V3. So V3 was at level 3, the other one is at level 1, so we continue the execution at level 1. Now, there are a few invariants that are holding in SAT solvers, which are very useful. For example, the first one, well, you don't imply bullshit. So basically, if you imply a literal, it means that there is a clause that implies it. Second, the trail follows the topological order of the implication graph. This is relevant for conflict analysis, and we will get back to it a bit later. And lastly, this is the bread and butter of propagation. It's strong watched literal. It states that if one of the watched literals is falsified and propagated, the other one must be satisfied. And with this, we ensure we don't miss any implication nor conflict. Okay, let's be greedy. Let's backtrack less. Because in our example, actually V2 is irrelevant to the conflict. So this idea was reintroduced by Alexander Nadel in 2018, and we can actually just continue propagating at level 1 without touching the level 2. Sounds like a good idea until, well, you reach a conflict. Okay, what do? You will remove level 2. Okay, fine. We do this. Uh-oh. There is a problem. C4 does not satisfy the invariant anymore because V3 is indeed propagated. Where is the pointer? Pointer's dead. Okay, never mind. I am delighted indeed. All right, so where were we? So C4, right, so V3 is one of the watch literals. It is propagated and it's falsified. So we will have a weak version of chronological backtracking, where basically what happened is that when we propagated V3, when we propagated V3 earlier, we were fine because V2 was satisfied at level 2 in clause C4. But when we backtrack, it's not true anymore. So let's do the ostrich algorithm and say it's fine. And we just weaken the invariant and the guaranteed we have. So with weak watch literals, what we have is you cannot have both watch literals falsified at the same time, which is enough for soundness. You will not miss any conflict, but you might miss some implications, hence the weak. So what can we do? We want to make it stronger. So first approach is we just fix the problem. And to do this, when we backtrack, we see literal V3, not V3, moved. So it was after V2, but V2 was removed. And so we will push back the propagation head by 1. Here it's only 1, but basically to the location of the previous decision, the last decision that was backtracked. And we will now, when we propagate the clause, when we propagate V3, we will detect that C4 implies V2. Right? And we get back the guarantees. This is nice, but what if V3 is 100 literals? Because here there's only 1, but it could be much more. So we don't want to repropagate all of this. So alternate solution is we use prophylactic approach and we just prevent the problem from happening altogether. And this is what we call eager strong chronological backtracking, and was fixed 2 years ago by Alexander and Adol again. And the idea is that when we detect that this literal is now called a missed lower implication, because we can imply it at a level lower than it currently is, then we just fix this. So we bring back to the minimum level possible. Now remember, I mentioned the topological order. And now we have a little bit of a problem because we changed the implication graph. So we need to reorder the trail. And these algorithms are very tricky to get right. And if you're in the context like an SMT solver, you don't want to reorder the trail. This is not so good. So we want to be a bit more conservative and less aggressive in the way you treat the trail. But this gives us a really nice guarantee that we actually have naturally non-chronological backtracking that is what we call backtrack compatible watch literals. So if you make sure that the satisfied literal is lower than the falsified literal, then you are sure that when you backtrack, either you backtrack the two of them, or you just backtrack the falsified literal and the clause is still satisfied. And so we will not miss any implications. So type 2 prophylaxis is we let the problem happen, but we just fix it cheaply. So the idea is we just add a new vector, and this is the contribution of this paper, with lazy reimplications. So when we detect a missed lower implication, we keep it in the fridge. We don't touch it. We just hold it somewhere that say V2 can be reimplied by C4 at a lower level. And now when the conflict happens, we don't need to repropagate V3 because we know that there is a clause here, C4, that implies V2. Okay, now I've used this example long enough. Let's change a little bit. Now this example is a bit more complicated, but this is very standard in chronological backtracking, is that the levels of the trail will change and alternate. So 1, 2, 1, 2, and so on. And here we have detected already one lazy reimplication. So let's perform conflict analysis. So we start with the original clause, which is V6, V5, not V7. And we will replace V7 by its reason, then not V5 by its reason. And here, usually we would stop. We have found our first UIP. Okay, but what will happen? Now you backtrack to level 2, to level 1, and you will imply V3. But we know that not V3 is also implied by the clause C6. So two solutions. Either we accept it and we say, well, I'm happy with this clause and I will perform conflict analysis again when I detect it as a conflict. Or alternatively, you can just continue the conflict analysis because we know an extra reason for it. And in the end, we get this clause, which I will boldly state is better than the one we had before. Okay, so basically, what do we have in this lazy replication vector? We have reasons. So this is an implying clause, but further, we have the guarantee that it implies the literal at a lower level. And with this, we can weaken the backtrack compatible invariant, which stated that the satisfied literal must be satisfied at a level lower than the falsified literal. And we can say, okay, either that or it is registered as a mislabel implication for later use. So to summarize the contribution in terms of code, so knapsack was written from scratch and supports everything except eager strong chronological backtracking because it's very tricky to do. And we have implemented lazy strong chronological backtracking in both catechol and glucose. So here we count the number of propagations performed by the solver with each of the variations that are supported in knapsack. And in red is the new approach that performs significantly fewer propagations. And the reason is if you have basically, we don't have to repropagate the V3 in the example, and this actually saves a lot. Now, of course, everybody can write a trash solver and say, well, I made it a bit better. So that's why we actually did it in the real solver. And we see, okay, the results are maybe slightly worse than the original catechol, but we did not optimize every option according to that. And the difference is quite small. So in the more recent set competition benchmarks, chronological backtracking did not seem to have a super strong impact. And this is reflected in this approach. However, it performs arguably better than Inger's strong chronological backtracking, which was actually removed from catechol because it's too complicated. So to summarize, we have the CDCL algorithm. Either we take the easy route. I mean, non-chronological backtracking is still not trivial, but let's call it the easy mode. Or we want a less aggressive way of backtracking. We can do the weak chronological backtracking, which in my mind doesn't make a whole lot of sense. So it is pretty easy to implement, but I marked it as medium hard because basically since you have very weak invariants, then all the machinery that runs around it is more complicated. If you do the restoration, strong chronological backtracking is basically the same implementation, but you push back the propagation head and you get better guarantees. Or you want to go for the very strong guarantees and go with the eager reimplication or our work, which is a little bit easier to write. So, I still have a lot of time actually. So if you have questions, that's good. So basically, we have formalized like a new dichotomy for all the chronological backtracking variants motivated by invariants. Everything was implemented and tested and experimented on. And that's it. Thank you for your attention.
So we have plenty of time for questions.
So you only use the decision level in your invariances in your implementation. Would you also need the trail level of these literals or not? Is it completely because you want to avoid the somehow this sort of like out of order thing?
It's actually the same. In our invariants, the level that we consider is the actual level of the literal. So inductively, it's the maximum level of the literals that imply that new literal. So
no, what I mean is like for some of these techniques to make them sound, you actually need the relative order of the literals on the trail, but you have a more partial version, at least on the slides, which only talks about the decision level, right?
Yeah.
That's enough in the implementation?
Yeah.
Okay.
I mean, in knapsack, that's how it works. I know that in catechol, Matthias had to work a little.
My question.
Had to work around a little bit. I don't know all the implementation details there, but in knapsack, there is no such thing as the order level or.
Right. Other questions? Let me ask a question. So in what you call the strong, if you can bring back the picture,
Which one?
all these features or variants of flavors of chronological backtracking.
The diagram or the table?
The diagram.
Okay.
Yeah. So here. So I also had to during conflict analysis, I had to continue when there is a conflict and then stash all the conflicts and they pick the one which brings me to the earliest level. Otherwise, the invariants are broken. So I'm wondering what you are doing in this new approach, Lazy.
So yeah, I struggled with that also. So I tried implementing eager strong chronological backtracking in the Verity, the solver, the SAT solver from Verity. And I also struggled a little bit with this, but you can just get over this by not considering the literal propagated until it is actually propagated. So if you have a conflict, you just, how to say, you take the first conflict, you stop, but then you don't consider the literals to be propagated anymore. So it's not a problem. So you will check again. If this literal is not backtracked, you will check again.
So essentially, you will backtrack and then you will rediscover the other conflicts. Yeah.
So you could also go all the way. But in this case, I don't think it would be a big problem because when you don't do the things eagerly, you will not have to deal with the chain of reimplications. Because if you reimply eagerly, you will have a bunch of stuff on the trail that will move. Considering the example here, for example, if there was no conflict here and you just reimplied v3, you would also have to reimply v5 and to reimply v7, right? In the lazy approach, you don't need to do this. This will be done naturally by propagation.
I know, but because Florian is here, who implemented this in his master thesis, so he refined that you don't need to do this.
So you refined so you mean you refined the multiple conflicts thing, and you stop at the first conflict? Okay, I'll look into it too. If there are no questions for the audience, I'll ask another one. Okay. So regarding the trail, the data structure.
Yeah.
So I used the linked list instead of array. What did you use and why?
So I used an array because there is no need to reorder the trail. So actually, if you go forward when you backtrack, so you can either backtrack from the right or from the left. Conceptually, it's the same thing because you can consider backtracking as an atomic state. So you just go through the literals and then you replace them, and that's linear and that's no problem. So you don't need a linked list for this. And also the argument is that I kind of learned these techniques in Verity SAT solver, and there are, I think, 1,200 references to the trail within the theory reasoners. So I definitely don't want to change that data structure.
I see. And you also said that it's kind of better for SMT. You expect it to be better for SMT. Can you explain why?
So we have not performed experiments yet. This is work in progress. But basically, when you reimply stuff, you almost always need to reorder the trail. Now, why you would say that when you backtrack, you also need to reorder the trail? In some cases, if you backtrack lower than the last thing you reimplied, say, for example, here, you could reimply v3, but then you learn a clause that is unit. Therefore, you don't need, you will backtrack to level 0. So reimplying v3 and asking the SMT solver also to update its internal state would be a bit of a waste of time in this case.
You mean that there are less, the SMT solver would need to work less to adjust itself, right?
That's the intuition. Now we would like to experiment and actually check this empirically, but that would be the idea.
Okay, thanks. So further questions? All right, if not, then let's thank the speaker again. We have a half an hour break.
Again, the usual set of announcements. Thank you so much for following all TCS security protocols. Thank you for your cooperation. And of course, we have a tea break now. You all can proceed and have tea there. Once again, a reminder for the cultural program. We have done this setup. It's a very interesting prospect. So looking forward to see you there. There are, of course, meeting rooms with whiteboards. They have been booked in our TCS research block. If you want to use some, please talk to our volunteers. And speaking of volunteers, the next session chair and speakers are requested to contact Abhishek and his enthusiastic group of volunteers for more information.
Test, test. 1, 2, 3. Hello.